Right, so we're told that f of x is equal to x cubed plus 4x squared plus x minus 6. And we're asked to use the factor theorem to show that x plus 2 is a factor of f of x. Now what some people do is they go, right, I've got to show this is a factor, let's start dividing. But that wouldn't be using the factor theorem. So what we actually need to do is, if we want to show x plus 2 is a factor, we want to show that if we sub minus 2 into this, then we get 0. And if you do that, you can see I've put minus 2 in and it does indeed come out as 0. And so that shows that x plus 2 is a factor. Okay? So now it asks us to factorise f of x completely. So there are a few methods for this. The one I'm going to go over is the box method. So if I've got a cubic and I'm dividing it by a linear term, the answer I'm going to get is a quadratic. So when I draw out my box, it looks like that. And so we want to get x cubed. So I'd expect an x cubed in that box. So that must have come from x squared times x. So in this box I get 2x squared, but I want 4x squared. So we must have another 2x squared there. So that must have times x by plus 2x to get the 2x squared in this box. So then down here I can fill this box in with 4x. How many x's do I want? I want plus 1. So this must be minus 3x to give us 1x. And so that must have come from minus 3 times x. And the good thing is, if we're expecting this to divide in exactly, what we should get in this box, which is minus 6, should give the same as the number at the end, which it does, and that makes us happy. Okay, so we know that f of x is equal to x plus 2 times x squared plus 2x minus 3. Then look to see if this factorises, and it does. X plus 3, x minus 1. Part B done. Part C says write down all the solutions to that equation. Well, we've factorised it, so we want when does this equal 0? Well, this is going to equal 0 when x is equal to, well, to make this 0, x has got to be minus 2. To make this 0, x has to be minus 3. For this 0, x has to be 1. Okay. Right, what about if we're asked to find a remainder? So let's find the remainder when f of x is divided by x plus 1. Okay, so what we'd do is we'd do the same thing. We would put minus 1 in, so we'd work out f of minus 1, which gives me minus 1 cubed plus 4 lots of minus 1 squared plus minus 1 minus 6. And so that would be minus 1 plus 4 minus 1 minus 6, which is a total of minus 4. So therefore the remainder is minus 4. Right, let's quickly go over logs. So remember, logs come from powers, so our rules of powers will help us remember our laws of logs. So, adding powers came from when we were multiplying things. So log a of x plus log a of y is log a of x times y. Subtracting powers came from dividing things. So log a of x minus log a of y comes from becomes log a of x over y. And finally, a power of a power, that's multiplying powers, and so k times log a of x, we can move the power up and make it log a of x to the power k. Right, let's use these three things to help us solve this question then. Well, the first thing I notice is I've got this 2 at the front that's not very helpful. So let's move that up and make this log 3 of x squared. Right, next thing I notice is we've got a subtract here, so that means we can put these together and make this a divide. So we get log 3 of x squared over x minus 2 equals 2. Right, now this is the tricky bit. What does this mean? This means that 3 to this power equals this. Well, what is 3 to the power 2? That's 9, and so that must have the same value as 9. Well, to show that, we just write down x squared over x minus 2 equals 9. And that's because that is 3 squared. what can we do here? We've got to rearrange this to make it quadratic. So we get x squared equals 9 lots of x minus 2. So we get x squared equals 9x minus 18. Rearrange it, x squared minus 9x plus 18 equals 0. And factorise, I'll make that x minus 6 and x minus 3. So x equals 6 or done.
Right, onto the circle. Quite often in an exam, you're given it in this form to start with, and they'll ask you to work out the centre and work out the radius of that circle. Really straightforward, just using a little bit of C1 really. Collect your x terms together, so x squared and 4x, and your y squared and y. Now I tend to move this value over to the other side, just so it's out of the way, and I'm not having to think about it just yet. It's then a matter of completing the square on the x and completing the square on the y separately. We do that, half the x coefficient, and then take away 2 squared, and the same with the y, so half the y coefficient, so 9 over 2, take away 9 over 2 squared. We've still got this minus 4 still over this right hand side. We then tidy up our sort of constants really, and move them all over to the right hand side. So minus 4, take away 81 over 4, it's 97 over 4. Still got the take away 4 here, and when we tidy this up, it comes out to 81 over 4. Now from this we can pull out the centre and the radius. So that bracket is 0 when x is minus 2, gives us our x coordinate. That bracket is 0 when y is minus 9 over 2, gives us our y coordinate of the centre. And the square root of 81 over 4 gives us our radius. In an exam, as long as you're clear, as long as you're concise, as long as you're careful, again, a nice set of marks to get would turn up quite early in the exam. Right, just 3 circle theorems tend to come up, and you just got to look out for them really. This one's a key one. Sometimes they give you 3 points on a circle, and if you're asked to show there's a right angle in those points, straight away you're going to know you've got a diameter. And that allows you to find the centre, it allows you to find the radius, rather than messing around with quite heavy algebra to find the equation of that circle. One to watch out for in the exam. Another one to bear in mind, sometimes you're dealing with tangents, aren't you? And we're after, maybe they give you the centre and they give you a point, and you're asked to find the equation of that tangent. And it's just using a little bit of C1. We can get that gradient there of the radius, and then we can do the negative reciprocal to get the gradient of that tangent. Then allows us to find the equation of the line. Just watch out for that. Be careful, they sometimes ask for the equation of the normal. Well, that actually is the equation of that tangent, or the diameter, isn't it? Just think carefully. Nice picture will help you loads. The last one, and this one actually again is quite common. Drop that line in there. Tangents from the same point are equal in length, and it also gives you a right angled triangle. And again, quite often you know that length. That length you can calculate, because they tell you that point, and they'll sometimes ask you for this length here. Again, a nice clear diagram, get your right angles on. Other than that, it's very straightforward.
Right, okay, so I've got here the binomial expansion. So I've got taken the 3 kind of formulas you're given out of the formula booklet. The first one, a plus b to the power n, that's the one I usually use for C2. The last one, which is 1 plus x power n, which is really handy if you've got a 1 at the front of your expansion. You can use this formula. And sometimes, on the harder questions, you might have to use this formula for NCR, the choose function here, using factorials. Okay, I've just picked 2 quite basic but quite common binomial expansion questions. So the first one, we're given this 2 plus a quarter x to the power 9. So we've just got to expand that. So I'm using the first formula at the top, but I actually think about it slightly differently. I think about it as 2 things. I've got 2 as one thing and a quarter x as another thing. So I always start off with the first thing to the highest power, so the power 9 that's given up here. So 2 to the power 9. Then I started in my combinations function in, so I've got 9c1. This is like 9c0 here, but that's just 1, so we don't need it. 9c1. And then I have my first thing 2, but instead of the power 9, I've got 1 less to the power 8. Then I bring the other thing in, a quarter x to the power 1. I notice I'm using brackets, so those two things are separate. Then we're going to look over here. We've got 9c2 now, and we've got 2 to the power 7. Notice the power's going down by 1 again. And a quarter x, but this time squared, and that's the whole thing, whole of a quarter x, all squared. And then we've got 9c3 for the next term. Notice this number's just going up along the bottom of the combinations function. And then we've got 2 to the power 6, 1 less power again, and I'm bringing the power up on the quarter x to the power 3. Now in the question, it asks us to find the ascending powers as far as x cubed, so I've gone up to x cubed there. So that'll be enough. I'll put block ellipsis to the end plus dot 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 just so it could continue. All I go then, I basically go and sub in all the numbers. I don't plug it all into my calculator because I've got to be careful. That's a quarter x to the power 1, so just a quarter of x. But quarter of x to the power of 2, I've got to square a quarter and I've got to square the x as well. Power 3, I have to cube that, and I cube that as well. So I keep them all separate. This is the line where I've got my expansion. Okay, I've got my 4 values there. It's interesting because it goes up to x cubed, but there's 4 values. A lot of people think there's just 3 values because of the 3 in the x cubed, but you've got this value where it's x to the power 0 effectively. Well, the next question is quite interesting. We have to estimate the value of 2.025 to the power 9, okay, using this. And if you look at our original question, we've got something to the power 9. So I just said, well, okay, our question to the power 9, when's that equal to 2.025 to the power 9? Okay, well, the raised to the power 9, so I can get rid of the powers. I can take 2 off both sides. And instead of putting a quarter x, I changed the quarter to 0.25 because that looked a lot like what was happening here. And I can see quite easily, I could do a division if I wanted to, but x is 0.1. Use the x's around 0.1, 0.01, somewhere there. So I want to use the estimate when x is 0.1 in my expansion to work this out. So I use this expansion here and I just put 0.1 anywhere where x is. And I've got to show that. I can't just type it in my calculator. I've got to type it in my calculator and write it down to get the mark. And there we go, there's my estimate. Now if you're unsure in the exam, type this in your calculator and see how close you are. You shouldn't be too far away, so that's a good little check there. Okay. My second example is a lot shorter, but it can be more complex if you don't look at it the right way. So this time we've got an expansion, but we don't know a value in the middle of it. Okay, so when I'm expanding things, and I'll just do it normally, that's the first part of the question. This time we have a 1 at the front instead of a 2, so we could use the other formula, but I'll use the one that I'm used to using. And it's very similar kind of expansion. But just be very careful, like here we've got px all squared, so over here we get p squared x squared. Make sure you type all those combinations into your calculator correctly, just be careful with it. So I get this expansion here. Okay, so I'll look at question B. There are first 3 terms are 1, 36x and q squared. Well, I've got the 1 at the front. I haven't got 36, I've got 9p x. Well, that 9p must be 36. Okay, so I said that 9p was 36, give me p is 4. And then look at the x squared term, that's q. Well, I haven't got q, I've got 36p squared, so q is that 36p squared. All I do then, I plug in my 4 that I've just worked out for the value of p, plug it in, 576, done, nice and easy. That's quite a common question. There are some harder variants on these, so make sure you practice these quite a lot, but these are the usual kinds. You'll always get asked something to expand it, then you might have to do something a bit afterwards. Okay. Right, okay then, so I'm going to have a quick look at the radian measure part of C2. So first of all, make sure you know what the difference between a sector and a segment is. So a sector is the whole pizza slice, and you might call an arc length L, radius R, obviously the whole circle if there was one there, and you've got theta, which will be measured in radians, okay? You've got a segment, which is if I had a sector, and I chopped off the triangle by creating a chord there. This bit here is a segment, like an orange segment on a Terry chocolate orange. Well, there are other kinds of chocolate orange available. Right, okay, so these are all the formulae that you need. Okay, first thing to remember, when converting between degrees and radians, 180 degrees is pi radians. So you can use proportions, so you can double that and say 360 degrees is 2 pi radians. Okay, you might need that. Make sure you know how to put your calculator in radians mode, because all the calculators in here will be in radians. It's just if you're using, like, for example, a sine further down, you need to make sure your calculator's in radians. Okay, so the first one is the area of a sector is a half r squared theta. Okay, and that theta has to be in radians. So find the area of that, half r squared theta. There we go. Okay, arc length, just r theta. But remember, that only gives you this bit here. Okay, now if you want to look at the whole perimeter, you're going to have a couple of radiuses on as well. Okay, radii. Right then, so we're moving on now. We've got the area of a segment. Now I just think of it as the area of a sector, take away the area of a triangle. Okay, so it would be the area of a sector, take away area of a triangle, which is half AB sine C, which I've put down there. Okay, sector, take away the triangle. If you put them together and do a bit of factorising, you can write that as half r squared times, in brackets, theta minus sine theta. Okay, make sure you're in radians. Last bit, we've got to work out the cosine rule sometimes. Now this might come when you've got this sort of triangle here and you know 3 sides, and you can work out the angle just there. So you can use cosine rule to do that. So make sure you remember that. It's just at the bottom there. A squared equals b squared plus c squared minus 2bc cos a. Done. Okay, I'll come back in a moment and I'll show you a couple of questions where you'll be able to use these. Okay, so I've had a look at one of the questions here. This is classic radians questions, and you can see on this one you've got a triangle with a sector within it. Okay, and that's the key thing to notice. So you can be asked for a few different things. So we're after an arc length, so that one we're going to use r theta. We're after the area of r at the end, so we'd have to maybe do the whole triangle, take away the area of the sector, and also we're after a perimeter of r, so we'd have to be careful on this one, because we need the arc length we just worked out. You'd have to work out that little bit. You know, that whole length's 11, that's 8, so that'd be 8 as well. And you can work that out by maybe using the cosine rule. So this is a really nice question because it involves pretty much all the formulas that I talked about earlier. Let's have a look at another one. And this is kind of the other way round. So you've got essentially a sector and then the triangle's marked inside of it. So you've got to use quite a lot of things. To find the angle here, you've got 3 sides. You probably want to use the cosine rule. And you've got to find the area of the whole sector, so that's half r squared theta. And we've got a few other things to find, so we've got to find the area of the triangle, that's half AB sine C. And also we've got to find the area of the segment, so you might have to take them 2 away, or you could use that other formula there. And then be careful when they ask for the perimeter, because a lot of people just work out the arc length, but remember you've got to add on the 2 lengths from the outside. So that's quite a classic radians question. Obviously there's quite a few variations, but remember, just look out for those triangles and those sectors, which ones I've got to add, which ones I've got to take. Just be careful with them.
Now, proof of the sum of a geometric series. Now, first thing to do is obviously we need to write the sum of the series by adding together the individual terms. Now, firstly, A, the first term, just like with arithmetic. Now, the difference is we use R for that common ratio, that value we multiply by to get from the first to the second, second to the third, etc. Hence why we've got AR is squared. And this obviously continues until we get to the last term, which is AR to the n minus 1, because we're going to multiply by R n minus 1 times. Now, the key here is once we've written it term by term and we've got our sum, we then multiply this whole series by R. So we got R Sn and then AR squared, AR cubed, plus all the way to the last term, times by R to get AR to the n. Now the clever bit, we take these 2 and we subtract them. Now you've got to look carefully because we could subtract them either way. I've chosen to do 1 take away 2, which then gives me Sn minus R Sn. And then the clever bit, grab my pen, top take away bottom, all of these terms disappear, and it leaves us with A take away AR to the n. Brilliant. And we're left with just this. Factorise both sides, take Sn out on the left, take A out on the right, and we do our last bit of division, and we smile to ourselves. That's how simple it is. If I decided to subtract the other way around here, did 2 take away 1, the only difference would be they would be the other way around and that would be the other way around. But in essence you get the same proof. Easy peasy. Right, just a quick example just to show you the type of thing you could be up against. Relatively straightforward. First 3 terms of a geometric series are 18, 12 and p. Now straight away you need to realise that to get from 18 to 12 is the same ratio as to get 12 to p. Now what they want us to find, they want us to find R, this common ratio, they want us to find the value of p, they want to find the sum to first 15 terms and the sum to infinity. I'll come to that in a minute. Now dead easy, to get R, second term divided by first term, 2/3. Yeah, leave it as a fraction, makes it easier to use. Then to get P, well, because that common ratio takes me from one term to the next, I can take my 12 and multiply it by the R I've just found. So 12 times 2/3 gives me the value of 8 for P. Dead easy. Then we want the sum to 15. Now, we had the formula before, didn't we? A, it was 1 minus R to the power of n, number of terms we want, divided by 1 minus R. So all I've done, right at the top, write my value down of A, write my down value of R. Been a bit naughty actually, because I should write my value of n as well, just to remind myself what I'm doing. Plug it carefully into the formula and then it's all down to how you use your calculator. Fractions, get that in brackets, otherwise you run the risk of it only being 2 to the power of 15. Brackets around everything that you think is important, and we get the value out, 53.9 to 3 sig fig. Not difficult. Sum to infinity. I haven't spoken about this formula yet, but that's it, you're given it, it's on your formula sheet. A divided by 1 minus R. It only works if the value of R is between -1 and 1. Alright? Because the terms get smaller and smaller and smaller as they get bigger, which means we can work out the sum to infinity. After that, it is just a bit of plugging in and getting that value of 54. Really straightforward. The only time geometric series get awkward is when you're having to deal with those months or years or values. You've just got to think carefully about how you're putting it together. Easy peasy with an examiner.
Okay then, so I want to have a look at some of the little bits of trig in C2. So first of all, I'm looking at y equals sine x, and I'm looking at the graph. Now remember, this graph does continue forever and ever in each direction, but I'm just looking between 0 and 360 degrees. I just remember it changes every 90 degrees, and going up from 1 down to -1, goes through 0 quite a few times. Remember, these could be in radians as well, so 0, 180 is pi, and 360 is 2 pi, so make sure on these questions you check your calculator is in the right mode. Now, a lot of people get confused. At the end of a problem you get sine x equals something, okay, a number between -1 and 1, and then you inverse. Your calculator will give you an answer. Now you can get another answer by doing 180 minus the one you've just got. So you get like this pair, and this comes from just over here. If we read off one answer, there's another one over there, and the difference between them is the same. I can actually just draw that on. Your calculator does it, it'll go across, it'll find a solution there, there'll be another solution over there, and this gap here will be the same. So that's why you do 180 minus answer. Okay. Once you've got those pair of solutions, you can plus or minus 360 from them to get as far as you want, depending on what range they ask for in the question. Okay, looking at cos, it's the same graph, but it's just shifted along a bit. So it starts at 1 and then does the whole wave, and it does continue for and over, and that's what it looks like. Remember the cos bucket, it looks a bit like a bucket. Now this one, when you inverse cos x equals something, you'll get an answer on your calculator. This time we do 360 minus it, and that's because if you read across from an answer here, the other answer will be over there, and once again by symmetry, these bits are the same. So that answer there, take it off 3, so you've got that one there. Okay, and once again, once you've got that pair of solutions, you can add or take 360, don't even know how far your range is. Right then, so tan, bit of a mad graph over at tan, and we've got these asymptotes at 90 and 270. The main thing about it is it repeats every 180 degrees, and it would carry on the same pattern. So when you inverse it and you get an answer, all you do, you add 180 degrees to your answer. Like for example here, add 180 to the next one, you can keep going, tell me to go the other way. Okay. And then two key identities. We've got cos squared plus sine squared is 1, which you can rearrange. So you want cos squared is 1 minus sine squared, and the other way if you want it. And remember, sin x over cos x equals tan x. Now these are important for when you're solving trig stuff. You can't solve any trig things unless you've just got one trig function. So either just sine, just tan, just cos. Quite often what will happen, you'll use this one and you'll get a quadratic in sine or cos to deal with. Quite often you'll swap this for tan, so you can get sine over cos equals tan, and then you'll be able to inverse something. And I'll show you a couple of those examples right now. Right, okay team, so we're going to have a quick look at some of the trig questions that you can be asked in C2. And I've just done my solution, as you can see. So the first question we're looking at is we've got a tan of some horrible stuff, 3x plus 20 equals 3 over 2. We've got to solve that between minus 90 and 90, so it's quite a small range, and we're going for 1 decimal place. So here's my solution here. So what I've done first of all is I inverse tanned 3 over 2. Now that gave me 56.3. I know 3x plus 20 is equal to that. Now this is where is the important bit of trig. As soon as you've inversed, you need some extra solutions. Now tan's easy. I can add 180s and take 180s. So I added a couple of 180s, and I could keep going with this. And then I took a couple of 180s off my original solution. Now I know in a minute I want to take 20 and divide by 3. So I was thinking, well, if I take 20 off each of these and then divide by 3, I want them within our range, which we said was between minus 90 and 90. That's why I've got so many. So what I did, I said, okay, well, I'll take 20 off each one. So I did that, and then I divided by 3, and I found these 3 were in the range. These two, were outside of the range. So I thought, well, that's brilliant, because I've got one that's too big, one that's too low. So obviously that means I've trapped all the ones I want in between them. So I did some extra solutions that I don't need, so I might even cross them out. So I've just boxed the 3 that I want. Okay, next question then. Looks difficult, but it's not really. We've got 2 sine squared x plus cos squared x equals 10 over 9. So what I want to do with that, I can't solve any trig stuff unless I've just got one trig function. So I'm going to swap cos squared for its equivalent in sine squared. So how we do that, I use this here. Cos squared is 1 minus sine squared. Okay, need to remember that. Just comes from the identity I show you that cos squared plus sine squared equals 1. So I swap cos squared for 1 minus sine squared. Now the only things I've got are sines in here, so I just simplified it down, and we end up getting like sine squared is 1/9. So when you square root, you get either sine x is a third or sine x is minus a third. Okay, so then I inverse that, and I got 19.5 inverse of a third, inverse sine of a third. But then I remember my rule: 180 minus that answer gets me the other one. Now I could add 360s to it, or take 360s from either of these, but our answers on this one, we don't need them all. We're between minus 90 and 90. So I think this 19.5 is going to work. I'd probably cross out this one here because we don't need that one. Okay. I need to check on these other ones as well, because here we've got minus a third. So I inverse sine minus a third. Minus 19.5, I want that one. I should circle that one. Definitely want that one. I don't want these other two. Now what I did 180 minus to get this one. I added 360 to that one. So these ones aren't in the range. So the answers for this one are going to be the minus 19.5 and the 19.5 here. The other ones are all outside the range. Okay, I've just demonstrated how we can get all the solutions there. Right, okay. Back to the question then. Now we're given this right beast here, and this one over there, we've got a 2 cos squared minus cos theta minus 1 equals sine squared. Well, first of all, I just want all coses. Could do with all sines, but I don't know what I'm going to do with that thing. So if I change this to cos, we should get a quadratic in cos, and that's what I did. So we can see here, I changed sine squared to 1 minus cos squared. I've rearranged to get this quadratic. Now you could go and replace this with 3y squared minus y minus 2 equals 0. Some people like to do that, but I just went straight into the factorisation. I've practiced these for ages, so I'm pretty good at them, but you can do that, switch if you need to. Then I get these two solutions, either cos theta is minus 2 over 3 or cos theta is 1. Okay. And then I've just inverse cos. I remember the rule for inverse cos. Take your answer, take it off 360. And I have the same there. Now I haven't circled the 360 on this one because if you look back at our question, the range for this one is from 0 to 360, but not including 360. So I've got all my answers circled in that case. Okay. Right, make sure you check the range, make sure you're careful with them. Now there's one more answer that I want to show you, one more type of question, because these come up quite often. This type of question, so you end up with a sine something equals 5 cos something, or something similar to that. Now, can be tricky, but isn't really at all. What you've got to remember is sine over cos will give you tan. So that's what I've done here. It's sine divided by cos to get 5. And look, let me see what I've done. Divided both sides by cos. So I've got tan theta is 5. They lead you into that with part A. You've got to find tan theta. Now remember, inverse tan. To find the other solutions, you add or take 180. I add 180 because look where the range is. I don't need to go into any negatives. There we go. Just thought I'd show you one of those types as well. Okay, thank you.
Okay, so we're going to look at differentiation here, and this is what I'd call your sort of starter basic differentiation, and it's going to test your knowledge that you know that a minimum has a second differential greater than 0, a maximum has a second differential less than 0, and this weird thing, we call it a point of inflection. It's where it looks like it's going to turn but doesn't, and that's got a second differential which is equal to 0. And if you ever get in that situation, don't worry, you can just find a point either side of your gradient, see what's happening, do a sketch. And what do we mean by second differential? It means differentiate once to find the gradient, differentiate again to check what type. So how does that look in practice? Well, here we've got an exam question. It says the curve C has an equation y equals 2x cubed minus 5x squared minus 4x plus 2. Part A, find dy dx. Well, just like in C1, I'm going to times by the power and then take 1 away from the power. So dy dx equals 6x squared minus 10x minus 4. Alright, so far, so C1. Next part, part B, it says using your result from part A, find the coordinates of the turning points of C. Well, those turning points are our minimum, maximum, or point of inflection. So, all I'm going to do is I know that when we have a turning point, that gradient is 0. So dy dx equals 0. So whatever I found it to be, I set that equal to 0 too. I simplified it by dividing by 2. I factorised it and I found my x values. X equals minus a third or x equals 2. Now, it asks for the coordinates. Do not throw away marks. If it wants the coordinates, it needs y as well. So I've taken my x values, I substitute into y, and I get my y value. So when x is minus a third, y is 73 over 27 by subbing it into my y equation. And then when x is 2, if I sub that into my y equation, I got y to be minus 10, so 2 minus 10 is my other coordinate. Alright, so all you've done, you've differentiated once to find the gradient, you've set it equal to 0 because it's a turning point, found your values of x and subbed it back into y. I've grouped C and D together because in C and D it says find d2y dx squared, the second differential, and it says hence, meaning use it, or otherwise determine the nature of the turning points of C. Sometimes in exam this will just be one part they lump together anyway. So all we're going to do, we've got dy dx equals 6x squared minus 10x minus 4. Part C, I'll just differentiate that. So my d2y dx squared is 2 times 6x, take 1 away from the power, just x, and minus 10x becomes minus 10, and minus 4 disappears. So I've got my second differential, and all I do to determine the nature of the turning points is shove in my value of x again. If in doubt, just put your value in. It works for finding y coordinate, for finding the gradient at a certain point. So at x equals 2, my gradient is 14, and we've said if the second differential is bigger than 0, we've got a minimum point. Make sure you put that conclusion to get your mark. d2y dx squared greater than 0 minimum. When I put in x is minus a third, I get minus 14 for d2y dx squared. So as it's less than 0, we've got a maximum point at minus a third, 73 over 27. Boom.
Okay team, we're going to have a quick look at one of the differentiation questions which people find quite challenging in Z2, is whether in context. So this time we've got a pencil holder in the shape of an open circular cylinder. radius r, height h. So I've done a little picture over here for myself. Look at amazing art skills there, and that'll help me. I find things difficult to visualise if I'm not drawing them down. We're told about the surface area, so that might be something we need to write down in a bit. And we've got to show the volume is this. So I think, well, they've talked about volume. I know the volume of a cylinder. It's pi r squared h. I don't know r, I don't know h, but it's there. Surface area, well, usually I'd have two circular bits, so 2 pi r squared, plus this rectangular bit here, which is if I unravelled this, I'd have the circumference along the top of the rectangle and the height still there, so 2 pi r times h. So I'd have to add that on for surface area. But in this one, it's an open cylinder, so that means that we've only got one of the pi r squared, so one on the bottom. So I crossed out that 2 there. So that's our surface area, pi r squared plus 2 pi r h. Right. So I've got two things that I could want to put together. Now I know about surface area, that's 250. It says in the question up here somewhere. Okay. So I put 250 equals that. Now what I've done, I've made h equals, and the reason is because their little formula for volume doesn't have a h in. So I said, well, if I make h equals there, I can then sub that in for volume, pi r squared times whatever h is. Plug that in, you'll get a load of algebra happening, and hopefully you'll get down to the thing that they've been asking for. Now a lot of people really panic if they don't get that. Right, that's 4 marks, right? This whole question is 11 marks, right? So if you think of those 4, you might have tried it, you might have attempted part of it, fine. Don't worry about it, you can still answer the rest of it, okay? It says, use calculus to find the value where there's a stationary point, or it might say maximum minimum point, where this v has a stationary value. It all means the same thing. You basically differentiate, that's what calculus means, either differentiate or integrate. So we differentiate, we set equal to 0. If you solve that, you get r equals 5.15. Now when it's equal to 0, you get either a max or a min. Now I know this is going to be a maximum because we've got a negative r squared, because it looks like that. It's one of those sad faces. But we might have to check it, and I think that's what's going to happen. Yeah, we do. Prove that we get a maximum. So how we do that, we find, as Mr. Barker mentioned, we find the second differential, and this will always be negative. You could put your value of r in, but I don't care. It's minus, and the value of r is positive, so it's always negative. Therefore, we've got a maximum. That's all you need to do. You can put your r value in, but that's enough to say it's always negative. Won't always be negative for every case in your situation, so maybe putting your r value in might be a good idea just to check. Okay. Then it says actually find the maximum value volume, and you're just using what you've done. So the maximum volume happens when r is 5.15. I put that into the formula for volume right at the start, and I get this answer 429 to 3 sig figs. That's it, easy. Check you're plugging things in the right places. Remember, differentiate set equals 0 finds maximum or minimum points. Second differential, you can check if it's a maximum. Negative for maximum, positive for minimum. Okay, and just check this last bit at the end that you make sure you sub it into the correct place. Okay.
Alright, this is a tasty looking little integration question. They've given us the graph of y equals x squared plus 6x plus 10, and they've given us the line intersecting with it, y equals 3x plus 20. I bet they're going to ask us to do some fun with this. Follow me. Alright, in part A, it says use algebra to find the coordinates of A and B. Well, if you can see, that's where the two graphs intersect. So all I'm going to do is set them equal to each other. X squared plus 6x plus 10 equals 3x plus 20. You solve it by setting it equal to 0. This factorises. I've got my x coordinates minus 5 and 2. I'm not going to be an idiot. I'm not going to forget to actually answer the question. It asks for the coordinates. So I'm going to plug it into one of my equations, the easier linear one, to get my y coordinate 2. Easy as. Alright? And that's marks to give you. That's about 3-4 marks right there. Now for part B, this is where they're testing you. It says use calculus to find the exact area of S. Now when we've got a graph and we want the area underneath it, we should know that we integrate to find the area under the curve. In this one, it's a little bit tastier. You've got a spot that there's a trapezium. Can you still see that?
Yeah.
So there's a trapezium between A and B. There's a curve underneath it. So if I find the area of the trapezium and take away the area under the curve, I'm going to be left with the area of S. Now, I'll talk you through the answer. Don't worry too much about my specifics, because in your exam you might have a triangle, you might have a rectangle, you might have a trapezium like me, but it's going to essentially be the same. You're going to integrate to find the area under the curve, and you're either going to take that away from a shape, or you're going to take a shape away from that. Simple as that. So in here, the area of trapezium, I've got half the sum of the parallel sides times the distance between them, and just be careful here, it's up the y-axis is parallel, distance between is x, and that all sorts out as 108.5, but where you're really getting your marks is over here, taken away from that the area under the curve. So I'm integrating between these points A and B that I found in part A. That's very, very common, so between -5 and 2, I'm integrating the function x squared plus 6x plus 10 with respect to x. So I'm just doing the classic of add 1 to the power, divide by the new power, add 1 to the power, divide by the new power, just simplifying that down as I go, and that's between -5 and 2. No c here because it's a definite integral, so there's no need to worry about adding c. Once you've done that, you just plug your values in. Plug in my upper boundary of 2, take away my lower boundary of -5. Once you've substituted those values into your integral, I'm left with 51 1/3. So my final answer for the area, I take away the 51 1/3 from the area of the trapezium, 108.5, and it leaves me with 57 1/6. Like I said, don't get too worried about the numbers. Just remember, you're integrating to find the area under the curve between the 2 points, and there'll often be a shape you add or subtract from. Easy as that. Follow me back over here though, ladies and gents, because how else could they try and trick you? Well, if we look at this very, very similar question real quick, I've got this cubic curve here, and what they want, well, first of all they ask us to factorise it, so hopefully we can see we've got x cubed minus 6x squared plus 5x, so I just pull out an x, leaving me x squared minus 6x plus 5 in the bracket, and I can factorise that to x bracket x minus 1, x minus 5. So I've picked up a couple of marks for being able to factorise. It says write down the x coordinates of point A and B. Just look at your graph, it goes through the origin, so I don't need to worry about when x is 0. Point A is the first point I get to, so that must be where x is 1. And point B is on the x-axis when y is 0, so it must be x equals 5. So I found my x coordinates when 1 and 5. And again, we picked up a couple more marks for that. Then the final part, it says the region R is bounded by C and the line OA, and the region S is bounded by C and the line AB. Well, all that means is this region here, the bit they've hatched it in. So it says find the area of the combined regions. All you have to do, it's exactly like the last example, but we're just going to be careful to split the two parts up. I'm going to do the region R, that's between 0 and 1. I integrate my function, that'll give me a positive answer because it's above the x-axis. And then I've got my region S, that's the bit below the axis between 1 and 5 I integrate, and because it's below the axis, it's a negative answer. But we know that area has to be a positive value, so we're just going to ignore the minus for this answer and add it to the value above. Take the modulus if you like. All booming day, that's all you have to do. Enjoy those 14 marks. Okay, ladies and gents, rounding off integration here with the trapezium rule. Now this is 6 easy marks if they give it to you, and the great thing is they often give it to you as well as another integration question. So if you can nail your integration, you can get 20 plus marks just from that. Now in this question they've given us this function here, y equals 1/10 of x times the square root of 20 minus x. Alright, and that's between 0 and 20. And they've given us this table, and all the values printed they've given to us already. We just need to fill in these 3 blanks here. And all you do is you plug the value of x into this equation, shove that in your calculator, and put your answer into the table. So when I put 4, 1/10 of 4 times the square root of 20 minus 4, out comes the answer 1.6, and it's to 3 decimal places, so I put 0, 0 in. I'm not making any silly mistakes to drop the marks. Alright, so we fill out our table by subbing in x, and then for part B, with the 4 marks, it's going to ask us to use the trapezium rule. Now some people get themselves in an unnecessary tiz. I'm going to make this simple for you, nice and crystal clear. So we've got our table from the question, and before we even look at the answer, this is how it works. The area of a trapezium equals the height divided by 2 times the 2 parallel sides added together. Well, the way that it gets confusing in here is actually, if the x-axis is running this way, people think of the height, the difference along the x is the height, and that's going to be the same for each trapezium. So really, all you're doing is your difference in x divided by 2 times by the 2 sides added. And if I see these 3 trapeziums here, when you see me lay it out added together, you can see the first height appears once, the last height appears once, every other height appears twice. So when you factorise it, it boils down to the difference in x divided by 2 all times the 2 end heights added together plus 2 lots of all the other heights. So it's as simple as that. So when we look back at our original problem, this is the table from part A. You can see for my area, it's approximately, because that's all it is, it's an estimation, a half, that's always there, times the difference in x, well that's 4 each time. So this half times the difference in x, all times, and in my brackets, I've got one lot of the first and last value, just happens to be 0 here, plus 2 times all the other values. So it's a half times the difference in x, all times the 2 end values added once, plus 2 lots of the other value. And that's approximately 43.86 metres squared. Thank you for 6 marks to my calculator.